Okay, hello everyone. I am just going to be recording for the last couple of slides that we didn't get to finish in class yesterday. We've got a practice problem for calculating a non-standard delta G, and then a couple of last summarizing points just to make sure we got those main ideas yesterday. So I'm going to share my screen really quick and show you this problem. We've got, we're calculating the non-standard delta G for the reaction between nitrogen and hydrogen gases to form ammonia at room temperature when initial pressures are 1 atmosphere of hydrogen, 1 atmosphere of nitrogen, and 0.1 atmospheres of NH3. So you'll notice the conditions that we're given here. We do have standard conditions for hydrogen and nitrogen, but not for ammonia. And so that's why this is a non-standard delta G. And in order to do this, we're going to need to find the delta G naught, the standard delta G, given this information about NH3, our delta G naught of formation. And then we're going to be using this equation down at the bottom. So we're looking for our non-standard delta G. We're going to calculate the delta G naught given our information about NH3. And then we're also going to need to calculate Q in order to substitute that in. So I'm just going to transfer this over to the whiteboard. We've got 3H2 plus N2, and we're making NH3. And they told us that our delta G naught of formation for NH3 is negative 46.1 kilojoules per mole. So my first step is I've got to find my delta G naught for this reaction. So that's going to be 2 times negative 46.1 kilojoules per mole. That's our products minus the reactants, which is 3 times 0 and 1 times 0. Remember, the delta G naught of formation for elements is defined as being 0. So I can calculate this, and my delta G will be negative 92.2 kilojoules per mole. And I'm just going to turn that into joules, 92,200 joules per mole. That'll make it so it's the same units as my R when I plug it into my equation. So now that's my delta G naught. So check, we got that done. And then we've got to find our Q. So they told us that we've got 1 atmosphere of hydrogen, we've got 1 atmosphere of nitrogen, and we've got 0.1 atmospheres of NH3. So to calculate Q, the first thing I'm going to do is I'm going to write out my Q expression using the balanced chemical equation. Always write this out symbolically before you plug in any numbers, because you will make mistakes if you don't. So in this case, we've got our pressure of NH3, and that's going to be squared because we've got a 2 as our coefficient. We'll have our pressure of H2 raised to the 3rd power, and our pressure of N2 just to the 1st power. So when we calculate our Q, we're going to end up with 0.1 squared, which is 0.01. Of course, it's just 0.01 divided by 1, so I'm not writing the 1 on the bottom here, but if we want to, we can do 0.01 divided by 1. So our Q is 0.01. So check, we've got our Q. Now we can plug this into our equation. Our non-standard delta G is going to be delta G naught plus RT ln Q. So I've got negative 92,200 joules per mole plus R, which is our 8.314 joules per mole Kelvin, times T, which is 298 Kelvin, they told us that in the problem, times the natural log of 0.01, our Q value. And our value for the non-standard delta G is going to be negative 103,600 joules per mole. So just to summarize here, we have our non-standard delta G. And the way that we got it was we used our equation that, combines our standard delta G and then adjusting for conditions that are non-standard with our Q and potentially also the temperature there as well. In this case, because we had the temperature at 298, it was really just our pressure of NH3 that was not standard. That was the only thing that was non-standard in this experiment. So that is our practice problem. And we also have some summary questions. The summary questions asked us about Q and delta G and how are they related. So conceptually, Q and delta G both do the same thing. They tell us about direction of a spontaneous reaction. This is our non-standard delta G or the delta G under whatever circumstances we have, the direction of the spontaneous reaction. So this is going to tell us if Q is less than K, then we go forward. If Q is greater than K, then we go in the reverse. And likewise, if delta G, again, this is the non-standard delta G, if delta G is negative, then we go forward. And if delta G is positive, then we go in the reverse direction. So these are related to each other mathematically by our equation, delta G equals delta G naught plus RT ln Q. That's how they're related mathematically, and conceptually, both of these things are just going to tell us the direction of a spontaneous reaction. Now, if we have standard conditions, then our natural log of Q, this whole term goes away, and we just get delta G equals delta G naught under standard conditions. And again, standard conditions are going to be 298 Kelvin, although sometimes that's not totally true. We kind of adjust for that sometimes. And especially the thing we want to watch out for is 1 molar of all aqueous solutions and 1 atmosphere of all gases. Okay, now what about if our system is at equilibrium? We've got delta G equals delta G naught plus RT ln Q. At equilibrium, by definition, our delta G equals 0. And our Q equals K. So what are we going to do here? We can actually rearrange this and we get our formula for delta G naught, the relationship between delta G naught and K. So how are K and delta G naught related? Mathematically, it's by this equation. Okay, but now what are they telling us? Both delta G naught and K are going to tell us about the relative thermodynamic stability of the products versus reactants. If we have a K that's greater than 1, or if we have a delta G naught that is less than 0, and again, you can see that why those are the cutoffs here if you look at the equation, but K is greater than 1, delta G naught is less than 0, that's going to mean that our products are favored. When we get to equilibrium, we'll have more products than reactants, and the products are going to be more thermodynamically favored. They're going to be more stable or favored by entropy. Something about them is going to be better than the reactants. And likewise, if our K is less than 1, our delta G naught is going to be greater than 0. And if that happens, it means that our reactants are favored. When we get to equilibrium, we're going to have more reactants than products, and the reactants are more stable than the products, or thermodynamically favored. Okay, so in free energy, they are favored. So this is the key idea here. You've been told up until now that your delta G naught, which is what you've been calculating until we started doing non-standard ones, you've been told that that means, that tells you about spontaneity. But the thing is, it only tells you about spontaneity under standard conditions when you've got 1 of everything. And that's not usually a situation that we encounter. We're more likely to encounter something where we don't have exactly 1 molar in 1 atmosphere of everything, right? In a real situation, in a real experiment that we were doing. So it's better to think of delta G naught more as an indication of the favorability of the products, which ones are products versus reactants. If your delta G naught is negative, it means your products are more favored. If your delta G naught is positive, it means your reactants are more favored. And the other thing is our delta G, the non-standard delta G, is the thing that tells us about spontaneity. And that's why it's related to Q. Q being less than K tells you the forward reaction is going to be spontaneous. And if Q is less than K, then delta G, our non-standard delta G, is going to be negative because the forward reaction is spontaneous. So those are just some big ideas to think about here with this. I hope that's helpful to see the problem worked out and also summarize those ideas about delta G and Q and delta G naught and K. Okay, have a great day.